In this section, we're going to look at how we can use a density function to calculate the mass of an object. And in single variable calculus, we can compute the mass of an object if the density varies only in one dimension. If it's varying in more than one dimension, then we need multivariable calculus. But we're going to look at some examples here where we can evaluate the mass of an object when the density varies only in one dimension. So in example 1, we're asked to we're asked to find the mass of a column of air, and we're given a density function for this column of air, which varies with the height above the Earth's surface. And so we want to find the mass of a column of air 2 meters in diameter and 25 kilometers high, with its base at the surface of the Earth. Okay, so I'm just going to start by just drawing sort of what that looks like. Obviously, I'm not going to be able to draw it to scale because 25 kilometers is pretty tall. So I'm just going to draw a cylinder to represent this column of air. And of course, I'm not going to be able to draw it to scale, like I said. But, you get the idea. So we have this column of air that looks like a cylinder. It's 2 meters in diameter, so its radius then is 1 meter. Okay, and it's 25 kilometers high, which means it's 25,000 meters, because we need consistent units, right? We're gonna, in order to calculate the density, which is or calculate the mass from the density that's in kilograms per meter cubed, we need all of our dimensions in meters. All right, so the idea here is to look at one slice. All right, so let's just look at one slice across this cylinder with a thickness of delta H. Okay, and so then the volume of that one slice is just going to be equal to the cross-sectional area, which in this case is a circle, so it's pi r squared. I'll just write it out here, and then times the thickness, which is delta H. Now in this case, r is 1, so we can actually just write that as pi delta H. Okay, and that volume is going to be in meters cubed. I'll just put that off to the side. All right, so from the volume, if density is only varying with height, and we take a small enough slice, then we can approximate the mass of that slice by taking the volume times the density. So let's do that next. So the mass of one slice is just going to be this density function. I'm just going to actually write it as delta H. I'm just going to write it as the function instead of because this is it's too long, right? It's a big looking function. It's a lot easier just to write delta H, and then pi delta H. Okay, so we take the density times the volume, and we get the mass of that particular slice, assuming that the density is constant, relatively constant, right? We're assuming that they're in that slice, delta H, the density is constant. Which, if we then add up all those slices and take the limit as the number of slices goes to infinity, then we'll end up with the total mass, right? So the total mass of this column of air, we need to integrate over the whole height. So from 0 to 25 kilometers, but we're going to write it as 25,000 meters. And we're going to integrate the density function, which, okay, I'll write it out, 1.28 e to the minus 0.000124 h. And then that times pi times, and when the number of slices goes to infinity, then this delta H becomes dH, right? Right, so that's so this is essentially representing our volume. Okay, and then of course this is density, because it's our density function, right? So density. All right, so now we just have to do that integral. So, you know, the numbers are kind of messy here. So I'm actually going to factor out this, the constant here. So I've got 1.28. And when I integrate this e to the minus 0.000124, I'm going to get this over a minus 0.000124, right? And then it'll be e to the minus 0.000124 h. Okay, and then I want to evaluate that from 0 to 25,000 meters. And when I do that, I just put it in my calculator to figure that out. I get approximately 31,000 kilograms. Okay, so there you go. There's an example.